You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Marshall Eubanks. Marshall Eubanks is Chief Scientist at Space Initiatives Incorporated, where he works on lunar communications systems and mission concepts to explore interstellar objects. He previously led interferometry programs at NASA's Jet Propulsion Laboratory and the US Naval Observatory, helping build the navigation and timing systems behind modern spaceflight and GPS. He is the lead author of the recent paper 3I Atlas, Direct Spacecraft Exploration of a Possible Relic of Planetary Formation at Cosmic Noon.
Dr. Marshall Eubanks, welcome back to the program.
I am not actually a doctor. I am sorry, but I am not.
Really? I didn't know that.
No,
You're
I'm a
master's.
physicist. I just have a master's, yes.
So that you know who was famous for that was Freeman Dyson. Also was master's.
And Bill Kalla also.
Yeah. And Dyson on purpose because he didn't like the PhD system.
And I could spend an hour talking about me, but I'm not going to.
Now, we have what is arguably the most interesting object to look at in the solar system in quite some time, at least since Oumuamua, maybe since Borisov. We can give Borisov a little bit of a boost there. But we have the third confirmed interstellar object we've ever seen, 3I Atlas. And it's turning out to be extremely interesting because it's possible, from a statistical point of view, that it's very old, significantly older than the solar system, and originates from an area of the galaxy called the Thick Galactic Disk, which went through a very interesting period called Cosmic Noon. Can you give us an overview of the idea of what Cosmic Noon was?
Well, the idea was that during the early period of the galaxy, and this is really early, so the galaxy looked rather different. It didn't have spiral arms. It had a higher gas density. And gas density means the production of stars and planets and planetesimals and things like 3I could be. And it's called Cosmic Noon. This, in astronomical terms, this would be a redshift of about 2 we're talking about. So about 10 billion years ago. I think in our paper we say 9 to 12 billion years, but something like 10 billion years ago. And a redshift of 2 is pretty far away. And so to see these things in the right now by looking out into space, deep space, they're all like far away galaxies that we can't see very well. And of course, we can't see what our galaxy was like directly at all 10 billion years ago. I mean, we don't have any old photos lying around. But the one interest, the consensus model for this is that when the universe formed, it was mostly hydrogen and helium, a little bit of lithium, maybe a little beryllium. And then the first stars, the so-called population 3 stars, formed, and they made some elements, and then things went on from there. And the Cosmic Noon was a period when this process was really in sort of midway, you might say. And so star formation was much more intense. The stars, in star formation, it's very common to have big stars and little stars form. The big stars form supernova fairly quickly because that's what big stars do. And then they both radiate, they both spread out the elements they form, but they also radiate, the supernova remnants radiate the other stars. That seems to have happened to the solar system in its early days. In Cosmic Noon, things were much more intense. There were predictions of maybe that any solar system forming then would typically have a temperature of 300 Kelvin, i.e. more or less room temperature, well, a little cold for room temperature, but more as the kind of temperatures you might have on the surface of the Earth, really different from the very cold temperatures that stars form in now. But also another interesting thing is that there's several ways to form elements, and they take different times. And the heavier elements, the iron peak elements as they're called, and the ones heavier than that, form in supernova that take a long time to happen. They're smaller stars like binary stars. They take a longer time to happen. And as a result, we think that, well, in fact, from stellar data, we know that the stellar spectral data, that in the Cosmic Noon period, the iron peak, all the really heavy elements were really depleted. They just hadn't had time to form yet. And so we see alpha elements, ones that are, excuse me, ones that are made by taking carbon and adding helium-4 alpha particle to it, and then taking that and adding another one. So you get like, you get like oxygen-16, carbon-12 to oxygen-16, and so on. And they should be enhanced in that, or relatively enhanced in that. And anything higher than that, like the iron peak and above that, should be depleted. So these things are different. And if you're really interested in astrobiology, you have to think, well, what did that do to the astrobiology then? Was astrobiology possible? You had different elemental compositions, you had different star formation, planetary formation going on. And the answer to that, I think, is we just simply don't know. I mean, there's some papers on this, but do we really know? No. And now we think what we're seeing in 3I. Remember, back a fair ways, but this became sort of pretty widely known in the astronomical community in the time of 1I, Oumuamua, pardon my Hawaiian pronunciation. The probability of an object that forms and is in a stellar system, like a comet or an asteroid or planetesimal, whatever, and then is lost from that system for whatever reason, whether it's because, the star explodes, or whether it's because the, two stars nearly collide and disrupt the system, or whether it's just the planetary formation stuff like we think happened in the solar system, where Jupiter and Saturn moved in and out, and they moved Uranus and Neptune in and out, and thus most of the early asteroids were sent into deep space, and a lot of them are lost. And all this stuff should be going on with early objects, and things will be lost. But the probability of one hitting or coming close to a planetary system, like within, say, a few astronomical units, is very small. And so it's most likely that what we're seeing with 3I right now is the conditions, the state it was in after it was born. It's something like a newborn baby. It has just been out there ever since. That doesn't mean necessarily things didn't happen to it early on. I mean, it might have formed from a collision of two planets or something. We don't know. But it's most likely that since whatever that was in the early days, 10 billion or so years ago, it's just been traveling freely. And then you might ask, well, why do we think this? And the arguments right now are primarily kinematic, and that means primarily statistical in nature. So they're not proof. They're just statistics. 3I has a very high velocity. And this velocity at infinity, the velocity it had when it was near the solar system, but before the sun's gravity started affected it, 58 kilometers a second. It's hard to get across how fast that is. That's multiple times faster than the Voyager spacecraft, our fastest spacecraft. That's something like 60 times faster than a typical fast rifle bullet. That's fast enough that you would pass an Earth radius in 100 seconds. So you would go past the whole Earth in 200 seconds or so, 3 minutes. Just the whole planet would go flying by. It's really fast, and there's another celestial happenstance here. It's going to pass by the sun closest on the far side of the sun, and there's no deep reason for that. It's like throwing darts at a dartboard. Sometimes the dart's going to hit to the right. Sometimes the dart's going to hit to the left. It's not like there's a deep reason. It's just, well, as it happens, the dart is hitting on the left and we're going to be on the right. So that means the Earth will not have a good view. It is not in a prime, box seat for the closest approach of this comet to the sun. And so we have to rely on other things. And we will get back to that. But the fact that the velocity is so high means, and the velocity out of the plane of the galactic disk is also high, both of those two facts together mean that it does not seem like this object is a thin disk object. The sun sits in a thin disk, which is this more or less plane. It's maybe 100,000 light years across, and maybe at most, it's again a statistical thing, but something like 1,000 light years thick or something like that. 3I Atlas's orbit takes it out to 1,000 parsecs or 3,000 light years. So it's further away. Now, again, that's a statistical argument. That's like saying if somebody is walking around near near a bank robbery, they might be a bank robber. Well, it's not proof. And what we're trying to do now with a whole bunch of astronomical observations is to try and get some proof.
Getting proof and more observations, because it seems to me the most important thing we could be doing in regards to this object is looking at it and looking at it repeatedly and watching it evolve and change as it nears the sun and begins to change its outgassing profile. What's particularly interesting is it's already a little odd for what it's outgassing, the lack of iron, yet you see nickel compounds and things like that. Well, it's interesting to wonder about things like a crust that it might have formed on it, being out in the interstellar medium so long and being exposed to, and reddened so much by cosmic rays. But what can we do as far as ground-based observations first from here on out and get as much data as we possibly can on 3i Atlas?
Well, 3i is also in the plane of the solar system, well, more or less. It's within 5 degrees of the plane of the solar system. It's a so-called retrograde object, so it's going through opposite to the sense of all the planets in terms of which way it's moving, but it's very near the plane, and that's actually good for observations. And it's going to get very close to the sun as it. We're not very close in a distance sense, but as seen from the Earth, it's going to get very close to the sun around the time of its perihelion. It gets close to the sun about a week before the perihelion. Perihelion is October 29th of this year. And yes, with comets, that's when you expect things to happen. That's when you expect the most observation, the most flares or jets. Borisov actually threw off a fragment just after its perihelion. It was a much smaller fragment, but it actually, they could see it separating off. And that could 3i do something like this? Of course, we just don't know. Comets are like cats; they do what they want and they have tails. One answer, the answer to any observational problem in astronomy is always more. Right? You always want more data, more frequencies, more observations, higher resolution. You always want more, but we don't have infinite resources, and it's useful to say, well, these observations would be very useful to have. These sorts of things would be very, very useful to have. Spectra, for example, very useful to have. And observations nearest to perihelion passage would be very useful to have. I'm not 100% sure about the crust idea. I've seen that. I forget which paper it was in. These objects will be in some sense meteoritically gardened, sort of like the moon is, because meteorites will hit them, interstellar meteorites that hit them. We actually have very little knowledge about what the flux of interstellar meteorites is. We don't know when it was last hit by anything, even statistically, I don't think we have a good handle on that. Of course, it could have been hit yesterday, but we don't know, right? So maybe the crust idea would work, or maybe it would be sort of like the moon, where you have some sort of just mixture of stuff and it's not crust-like, or maybe it's, if you look at all the asteroid surfaces we've looked at have been pretty different from each other. So I would expect surprises.
And you mentioned Borisov throwing off a fragment. I imagine that's on its way out too, along with Borisov. But the idea of a comet leaving a tail. We go out and we see the Perseid meteor shower and things like that, which are, a number of those are basically the tails, the past pathways of comets. Sometimes we even know which comet it was, and it's still, doing its thing. Will there be anything that we can study that this thing leaves behind in its trail as it outgasses further?
Well, I think yes. Now, the meteor showers you're talking about are all because those are repeating comets. They have come through the solar system more than once, and they leave debris. And basically you have sort of 3 kinds of debris coming off, or stuff coming off. You have the gas, so it has ice on the surface, and so water sublimates, and you have water vapor going off. You have dry ice, carbon dioxide, or maybe you have carbon monoxide, same thing going on. These things go out. The sun's UV photoionizes them, and they turn into a plasma, and that's the typically straight tail you see from comets. And a lot of times that's the biggest and brightest tail. And so a lot of times when you see a picture of a comet, there's a long straight tail. That's the plasma tail. All right, that is gas, and if you happen to fly through it, and we will get to that, if you happen to fly through it, you could see that gas, and you could see the magnetic fields and so on. You're not going to see that as a meteor shower. It's because it's molecules, or ions, single atom ions. And back in the days of Halley's Comet, people said, oh my goodness, there's phosgene and other poisonous things. We'll all be asphyxiated when we fly through the comet. Well, no, through the comet's tail. Well, no, it's actually a very, very good vacuum. It's just over a large scale, you can see it. And then there is the small stuff, the dust. So these are grains. I mean, they're about the size of cigarette ash dust. I mean, maybe nowadays not a lot of people haven't seen that, but very thin ash or dust of some sort, the sort of dust you might find on top of your counters or something, or behind the clock or something like that. Very thin dust. And that is actually affected by solar radiation pressure. And so that goes away from the orbit. And so that's typically a curved tail. And I believe are seeing both of those from Atlas right now, 3i Atlas. Now, I'm not an observational guy. I haven't been taking these observations, but that's what I hear. And also some coloring in it. That's also very interesting. And then there is the larger stuff. If you imagine just sort of you're heating up ice, water ice or CO2, whatever, and it has jets coming up. Well, if there are pebbles or rocks or whatever around that, they can also, and the attraction of the gravity is very low, so they can also be thrust off and you lose them. The comet loses them. And those tend to stay in the orbital trajectory of the comet. Those get spread in mean anomaly. They have very low velocities going off because they're heavy, and they're not very affected by radiation pressure from the sun or anything else like that. And so they just sort of drift along. And over time, those will build up, and that's what causes we think that's what causes most of the meteor showers. I mean, there might be other objects that are a little bigger that get pushed off to boulders or whatever. And so you might have the occasional large meteor, but that's basically the idea there. We don't expect to see that from 3i. However, we do expect to see the dust tail, the curved dust tail. We are seeing, I mean, there's pictures, I've seen some today from like yesterday or so. This is, it's growing. The tail is growing. It's like 2 arc minutes long, I think, right now. The dust tail and the plasma tail are there. They will likely grow. We, of course, can't really predict very well how much they will grow, but that's something we want to observe. The comet showers will not happen. And as it happens, I mean, it is very probable that 3i Atlas is leaving stuff behind it as it's traveling, and maybe stuff in front of it of pebble size and larger. The trouble is, we're not going to pass through the orbit in time. The Earth won't pass through, or near the orbit. Mars, as it happens, Mars just passed through where 3i Atlas is going to be about a week ago or something. It's not going to pass through it again for a whole Martian year. And by that time, whatever 3i left behind is just going to be long gone. However, that doesn't mean that all is lost, because 3i could have been, well, I mentioned it might be hit by meteors, interstellar meteors. That could have been going on for a long time. It could have been having stuff thrown off, probably not by heating, but by meteor hits over, billions of years. And so it should be, in fact, I think, surrounded by a cloud of debris. We know very little about this process right now, so we don't know the densities and all like that. But it means that it is possible that we will have meteor showers on either Mars or the Earth, or you could see them possibly hitting the moon if they're large enough, that will come about. And for the Earth, it'll be in December. This is actually all in the paper. And maybe the Mars rovers could see them. I don't know if they're planning to observe, but maybe they could see them. They would appear to, in the usual meteor shower fashion, they would appear to come from a certain radiant. We know where that radiant is. It's 19 hours minus 19 degrees declination. It's the place where 3i appeared to come from. And so if you're on the Earth, my guess would be the rate would be very low. So it's not like you'd see one a minute or even necessarily more than one a night. But, here's a case where amateur meteor observers, I think, will have an opportunity to do things, because they could go to Mars, obviously, but they could go to Earth, places on Earth, and say, okay, I want to look for these meteors and see if I see them. And even if only 1 or 2 were detected, I mean, again, these arguments are going to be statistical. If you see one thing that kind of sort of comes from the radiant, that doesn't prove anything. But if you see multiple ones that are coming from the same radiant, then yes, you could say those are coming from 3i. And, I think amateurs and also the professionals who are operating the cameras that, like the full sky cameras that look at the sky every night, I have no idea what the chances are. I really don't. Maybe it's near zero. Maybe it'll be obvious, and a lot of people see it. But I have a feeling it'll be a sort of occasional thing, but I think that's one of the things that the ground observers can do. Would this be a good time to talk about the general? Well, let's talk about let's talk about what we can do in space.
Let's transition to space and a spacecraft being in the right position to end up in that cloud that 3i Atlas leaves behind and use whatever instruments it can
Yes.
to take a look.
We are unlucky for the Earth. The Earth happens to be in the wrong side of the solar system. It's just, there's nothing we can do about that. It just is, It's just, like I said, if 3i had come through 6 months before or after, we'd been in a really good position. It isn't, and we aren't. However, we are also lucky in that there are a number of spacecraft that are on the right side of the solar system, so to speak, the 3i side of the solar system. And that is luck. I mean, we have all the spacecraft at Mars. We have the JUICE spacecraft that just had a gravity assist at Jupiter on the 31st of August. Or it's not at Jupiter, on Venus, and is going up, to another gravity assist, and eventually going on to Jupiter. We have the Europa Clipper spacecraft. We have the Lucy and Hera spacecraft. We have all these spacecraft out there. We have the Psyche spacecraft that's going to Psyche. All of these spacecraft happen to be on that side of the solar system. That's not a necessity, right? At a different orbital phase, Mars will be near the Earth, near opposition, so on the Earth side of the solar system. I mean, all of these things move around, but as it happens, there's quite a lot of numbers interplanetary spacecraft on that side of the solar system. And so early in July, 3i was discovered on July 1st. By July 2nd, it's moving so fast. By July 2nd, we were quite sure it was interstellar. I mean, that's of course a U.S. holiday period. It's also my birthday, and July 3rd. And it was about the 4th or the 5th before I realized, yes, this is a comet, and it's going to be on the other side of the solar system, and it's opportunities are going to be poor from Earth, but good from spacecraft. And so it just seemed to me, we being my company, Space Initiatives, but also the I4IS Institute. The Institute for Interstellar Studies and the Initiative for Interstellar Studies, which are the US and UK versions, respectively, we should look at this. We should see what the spacecraft can do. And we rapidly concluded that for imaging, the 3 spacecraft were Psyche and the spacecraft around Mars. Well, I say 3. The spacecraft around Mars, of which there are a bunch, and the JUICE mission. JUICE is right now not that close to where 3i is going to be, but it's climbing out of the solar system because of its Venus gravity assist, and it will get there. And Mars will have the closest approach. Psyche had the approach on September 4th. The Mars spacecraft will be closest on October 3rd, and the JUICE will be closest on November 4th. And I started sort of bugging spacecraft people saying, and I wasn't the only one. There were other people who were saying, a lot of people were focusing on Mars because Mars is going to be the closest approach in early October, but you have to make a case. And so I tried to make a case in the paper we wrote that, yes, this is probably a thick disk object. If it is a thick disk object, it has these certain characteristics. These are things we should look for, and that justifies using your spacecraft to look for them. And I can tell you that there are a numerous spacecraft team, a number of them have been really working very hard the last few weeks. I mean, the last month and a half or so, to try and do observations of 3i. It is not trivial. It is not, it's not like just saying, oh, I'm on a bus and I'm just riding by the Empire State Building or whatever, and I'm going to take a picture out the window. No, it's not like that at all. It's like I have this very complicated system that, is millions of miles, millions of kilometers away. I can't touch it. I can't fix anything if it breaks. I have to be very careful about using it. And somebody like me comes along and says, yeah, do something different. That is not trivial. That is, I really take off my hat to those people, take my hat off, because it's like they have been working hard. I hope they can all get observations. In some cases, I'm not even sure that they know whether or not they can get observations, but they're certainly trying. And so the periods are, early October and early November are And in fact, November 2nd to 25th are the periods when the Mars spacecraft and the JUICE spacecraft, respectively, will be getting their images and other data on 3I. And it'd be very, very good if people on Earth, including the amateur community, tried to take simultaneous observations during that period. Now, I can't, there's many, many people on Earth that have telescopes and stuff, and, both professional and amateur. And I can't say, oh, this, whether or not what you can do or not. But I know that, I'm sure that some of the amateurs are going to try and take observations of the tail and the like when it's very close to the sun. And I think, that they should. And I think anything they can do around that period could be especially useful. And there's actually, of course, two other things that spacecraft will do. And I will sort of do them in the order in which we worked through them. The solar probe, I call them solar probes, but they're solar observatories and solar missions. There's two solar missions, Solar Orbiter and Parker Solar Probe. And then there's a bunch of spacecraft, some in Earth orbit, some in Lagrange points or in other orbits that image the sun. Well, they don't have trouble taking images of things close to the sun because they got the cameras designed to do that. The question is, can they see 3I? And that'll depend on how big it is and how bright it is. Things are looking actually fairly good there, but we think that the recently launched Punch spacecraft array, which is actually in Earth orbit, could probably observe it and probably detect it. They can all observe it. I mean, it'll pass through all of their fields of view. The question is, will they see it? Actually, that's not quite true. It won't pass through the stereo A field of view we found. So stereo A can't even observe it potentially. But is it bright enough to see? Is it big enough to see? And well, we don't know yet. But there's another amateur community that looks at the pictures from these spacecraft, and they will for sure be telling us whether or not they see it or not. I have no doubt about that. But if they need to redouble their efforts, well, they should do that too. And those data will be very useful because those could be day by day. And so it'd be like when we can't see it from Earth, those could be like, here's a day-by-day record saying what's going on. The interplanetary spacecraft stuff will not be day-by-day. It'll be they observe it this period for a bit, and then they have to do other things, and they observe it this period for a bit. So it'll be intermittent. So I think that's useful. And then the last thing is, it looks like there's a possibility that Europa Clipper and Hera spacecraft and Lucy spacecraft could fly through the tail of 3I. Now, probably the plasma tail is the best bet there. So they could fly through the plasma tail. They might fly through the dust tail a little bit later because the dust tail will be curved away from the dynamics of it. And they will not fly. No spacecraft is going to fly through the orbit and get the meteor shower tail, if you want to call it that, the neutral tail, some people call it. That 3I is probably leaving behind. We don't have we won't be able to do that because we don't have anything in the right place. But I think it's a good chance that Europa Clipper and probably Hera too, because they're fairly close from each other, right, just by happenstance, could both see the tail. And there's another case, and that would be the first week of November, probably. Again, hard to predict comet tails. There's another case where, and that's when it's still close to the sun, but any amateurs or whatever who could observe the tail at that time, it'd be very nice to know what's going on. Now, I should say that the tail that people take pictures of is the tail that's visible, but the stuff that comes off, whether it's the plasma or dust tail, doesn't just vanish because we can't see it anymore because it gets too thin to see. It's still there. It's still going away from the comet, and I suspect that these spacecraft will not go through the visible tail. In other words, the visible tail won't reach out 1 AU. Europa Clipper will be like 1.2 AU away. So I don't think the visible tail is going to get that long. It'd be lovely if it was, but I don't think it will. But that doesn't mean the material won't be there. And so that doesn't mean their plasma won't be there, and their plasma instruments can't see this and say something about what they're seeing there. And that, of course, would be very, very, very nice. Whether they go through the dust tail, we're still trying to figure that out. And that would be also interesting because potentially you could sample it that way. I don't know how realistic that is. I don't know if it's going to happen, but we've been working hard too. And that's sort of the next thing we're trying to figure out. And they're actually working with some people in Europe, some collaborators in Europe. So we've expanded our team a little bit.
Well, speaking of Europe, happily, we now know by announcement by ESA that Mars Odyssey and Mars, what is it, ExoMars, are, or Mars Express and ExoMars rather, are going to attempt observations. So this is happening. It's beginning.
Yes, and we do not know about the Hope spacecraft, which is from the Emirates, or the Tianwen-1 spacecraft, which is from China. And I've actually tried to contact people at both of those spacecraft to see if they will observe, and to encourage their observations. And unfortunately, I've not heard much of a response. You know, there could be political difficulties there too. I don't want to get into that, but
Now, regarding tails and two separate tails. Now, in pictures of comets, including many wonderful amateur pictures of comets like Hale-Bopp, you remember that one back in the day? Spectacular. I photographed it myself.
I saw that with my naked eye.
Me too. Yeah, me too. Good one. You know, and it was, I watched it. It was very visible.
In fact, I remember I went to some opera or something down in D.C. and I actually saw it near the Kennedy Center with my naked eye. I was astounded.
I
looked up and there it was, you know.
Yeah, there it was. And I was actually observing it from St. Louis. And it was, you know, obviously St. Louis has a lot of sky glow, but there more so now than it did then. But there it was. And you go out and look at it every night. But I would also go out into dark sky locations and do long exposure photography with it. I actually still have those. One of these days I'll pull those photographs out. But the thing is that sometimes when you see these pictures of these comets in the past, you can visibly see in the photography, if not visually, the two different tails. Mm-hmm. You know, you see the chemical tail curling and then, you know, the dust tail, you know, going off. And this is actually something you can see, but probably not with 3i Atlas.
And that's actually what causes the anti-tails occasionally, where it looks like there's a tail in front of the comet. It's just a projection effect. You're seeing the dust tail, and you know the angles are such that you're seeing it projected.
That's an interesting distinction to make, because as 3i Atlas is showing us, there's really two types of an anti-tail. There's one where it's preferential heating causing gases to, you know, shoot forward, which is what's happening with 3i Atlas, which to me seems like a true anti-tail. And then there's the perspective effect, which isn't really an anti-tail. It's your perspective on how you're viewing it. You're seeing the comet's path is what you're seeing effectively.
Good point. Yes.
So I wanted to make that distinction that there are two types. Comets can do this two ways, and it is not rare for either. Comets do this, and a lot has been made about the anti-tail regarding 3i Atlas, but no, that's not that unusual, right?
I mean, none of the stuff I have seen with 3i Atlas, except for the chemical stuff to some degree, I regard as unusual. You know, I mean, its action as a comet seems, and I'm not, that is not my direct area of expertise, right? But I have been involved with this for a long time, and it just seems like really a pretty commonplace comet, as did the 2i Borisov. Again, I'm not talking about the chemistry. I'm just talking about, you know, they both had tails. They both, when they became active, all that kind of stuff seemed pretty normal, you know.
To me too, I was like, well, it's becoming active right about the time it should. It should start, you know, releasing CO2 and these things that they do. But the chemistry, that's interesting, because now we're getting a profile of chemistry. You know, you can compare it to objects ostensibly of different ages. Oumuamua and Borisov were both of radically different ages.
Yeah, we think 1i was pretty young. And of course, we never got a spectra from 1i, a real spectra. We don't know anything about what chemicals it had. I mean, we can guess, but
the only thing I ever heard, it was reddened, which is you expect that from the interstellar medium.
Yeah, I mean, that's kind of a spectra, but it's not like it tells you, you know, reddened doesn't mean, oh, it's made out of this. It just means, well, it's red.
Yeah, it just means interstellar medium. A lot of cosmic rays out there. Now, Marshall, the chemistry question, though, is perhaps the most interesting one here, because it is doing a few things that are a little bit weird chemical-wise, and it may simply be a product of age or in an environment it passed through or did something to it, you know, to make it look a little bit strange. Low CO2, low iron, that one's really puzzling, and things like that. What can we learn about that using the spacecraft and ground-based observations to get a characterization of the object?
Well, on the spacecraft side, some of the instruments we're talking about on both the Mars spacecraft and the JUICE spacecraft can look into the UV, and so they can see the areas where the spectral lines where, like you mentioned the lack of iron and the presence of nickel. Now, I should say that that is not an indication necessarily that of this iron peak diminishment that I was talking about, because, well, for one thing, nickel is also an iron peak element, so you expect them both to be diminished. But also, we suspect that the chemistry here is rather different. Although I have to say, the fact that the notion, I mean, some of the earlier comets, the one from 65, for example, got so close to the sun that they had iron and whatnot spectral simply because it was ionized. The iron was, melted and vaporized, and you had vaporized iron, and so you had spectral lines from vaporized iron. That's pretty hot. And it was a real surprise, I think, to the community to find that no, comets can do iron and nickel, and nickel seems more prevalent, even way out, multiple AU from the sun where it's not hot. There's just no way the iron on the comet is vaporizing. I mean, on 3I right now, or any time during its path through the sun, it doesn't come close enough. It comes a little closer than Mars, but Mars is pretty cold. I regard all that as is something of a mystery. There's some the idea that I guess you could say the consensus is that there's some element, some compound, some molecular compound that is both volatile and has nickel in it, and maybe also volatile and has iron in it. And these things are being vaporized on the comet, and then the solar UV flux disassociates the nickel or the iron, and you see it. And that sounds very plausible, but I don't have a really good feeling that we really understand it that well, in the sense of why are those compounds on the surface? What's causing this really? Is there something deeper? Or is this just a happenstance? But that's not going to, unfortunately, because I was at one point hoping it would, but it's not going to answer the question of like, well, is this an early alpha element dominated comet? Because if it's from the thick disk, it should be alpha element dominated. Now, alpha elements are like carbon and oxygen, and those are common. I mean, you have water, you have CO, and you have CO2. And I actually think that the better chemistry thing is you shouldn't have super volatiles. You shouldn't have things that, because in the models, the cosmic noon era, star formation should have happened in very warm regions. They should have had lots of, very high star formation rate, all very close together. Something like the I think it's called the Tarantella Nebula in the Magellanic Clouds, except more so, and so much more violent than the Orion Nebula star formation region that I'm pretty sure everybody has seen at night, and thus much hotter. Now, there's a paper that claims it might have been as hot as 300 Kelvin, i.e., above the room temperature. I mean, something like room temperature, above the melting point of water, and well above the vaporization point of water. I think that can be ruled out. I think the temperature, what we're seeing is lots of CO2. I mean, lots of CO2. Not too much water, but some water. Not less CO. So that's surprising. So that right there says that it came from a warm environment. It either came from early in some solar system, some closer to the sun, or stellar source of some early solar system, or it came from a warm star formation environment. And since we predicted a warm star formation environment, I kind of view that as, as sort of a win for our side, you might say. But it would have been about 100K, something like 100K. So that's certainly warmer than deep space, but it's not that hot. And so you get CO, but not CO2. Carbon monoxide, CO, is very volatile. It goes off first. And I don't see much sign of that. Now, as I was saying earlier, this is sort of science by press release. All of this could be changed by once the papers come out, and the papers analyzing the papers come out, and everything is digested and all like that. But that is just the feeling I have right now. I think we need more, though, to be sure. And I'm hoping that we will get that. When something is passing behind the sun, every telescope system has sort of the minimum elongation it can do. And once you get inside that zone, I mean, for the Hubble, it's 55 degrees one way, plus minus. That's very wide. Hubble basically will not be able to take more observations, I believe, until December of the Hubble Space Telescope of 3I. And Webb, its zone of avoidance started in August and will go into late December. So we're kind of up to the Earth telescopes and the sky telescopes. And I haven't heard anything from ALMA yet. ALMA ALMA can see some of these molecular lines up in the hundreds of gigahertz region. I'm really looking forward to seeing what ALMA says about this. I'm sure somebody's got plans to use ALMA. ALMA can actually observe, I believe, down to 15 degrees elevation from the separation from the sun, and so that means it'll only have about a 10 days, 2 weeks period where it can't observe through the eye. But some of the telescopes on the interplanetary missions, especially JUICE and some of the Mars missions, including the Mars MAVEN and the HOPE spacecraft, have the right kind of instruments, I think, that they could say something about what's going on. And there's another chemical that I really hope somebody detects and we can say something about, and that's PAH, or polycyclic aromatic hydrocarbons. And the PAHs are both hard to pronounce for me, and one of these things that they're kind of really mysterious. I mean, they actually were detected in space spectra in the infrared by spectral lines that nobody could explain. And if you know what a benzene ring is, it's carbon in a ring, and PAHs are basically benzene rings stuck together to form larger things. So you have lots of benzene rings, and so they have different modes of, the rings can squish like this, or the ring is flat, things can pop up and down out of the ring, and those are all those modes. I mean, it's very much like a weird musical instrument, like sort of a drum made out of metal rings. All these modes of excitation, just like modes in a drum, are effectively sounds, except in the with infrared light, it is a spectral line, but it's this. I mean, it's the same thing. It's the same basic physics in a sense. You're seeing these spectral lines from PAHs. For a long time, we didn't know what was causing it. It seemed very mysterious. These lines nobody knew anything about. Typically up in the so higher infrared, all the way up to 13 microns, I think. But now we understand a good deal more, and it seems like a lot of the carbon in the universe is in the form of these PAHs. That now, that doesn't mean that, if you go to Mars, you're going to find PAHs on the surface or whatever. No, I'm talking about the carbon in the universe, which is mostly in gaseous form out in space. There's a lot of this stuff out in space, and it's very, very common. And it's also present in, like planetesimals and star formation, and the different star formations do things to the PAH. They change. I mean, basically the temperature has a control on the size of the particles. And at one point I thought that there's papers that claim that the radiation environment can also change the size of the particle. I think that's actually probably not true. I think that I've been in contact with some experts in this, and it's really just the temperature. But that would be I mean, even if you don't believe the thick disk hypothesis, it would be very nice to know what temperature this object came from. And I think we're kind of getting that. And I think if we find PAH emissions, which again, I think ALMA could also see, chance of getting a handle on that. And one of the things I've been thinking about a lot is
polycyclic aromatic hydrocarbons. Now, these are interesting chemicals, and given that we're seeing them abundantly, we also see them in meteorites. We see them in, solar system comets and things like that. But these are also linked to potentially the origin of life, because we're dealing with the chemistry of carbon here. Now, what would a profile of that tell us from another star system, perhaps, especially if it's ancient, of what the conditions might have been like? And maybe, could the universe teem with life if there are PAHs everywhere?
Well, PAHs, of course, were really mysterious for a long time, and in fact, they're still pretty mysterious. They were detected. They were first, just as helium was first discovered, when somebody saw helium spectral lines in a solar eclipse, people saw weird, unexpected spectral lines in infrared data, and they didn't know what it was coming from. And for a long time, decades, it seemed nobody really could figure out what's coming from. And now we think it's all PAHs. And let me just say, it's just a little bit about what that is. most people who've taken chemistry know what a benzene ring is. It's a ring of carbon atoms around it. So it's six or something like that carbon atoms, and it's just a ring. A PAH seems to be just many benzene rings connected together to form kind of a carpet. And these rings have this carpet has modes in it. So it has a mode where the rings squish together, and it has other modes, and it has a mode where the one of the side of the ring is popping up and down. And just like in a drum, if you strike a drum, the surface moves, and that causes sound waves. Particularly if a ultraviolet photon from like the sun or some other star strikes a PAH, it vibrates, and that vibration, that sound, if you would, is not sound in hearing, it's sound electromagnetically, and that's infrared light, and we can see that. And I have not seen a claim of detection of PAHs from 3I, but 3AHs or PAHs, PAHs, are ubiquitous in the universe. They seem to be it seems like most of the carbon in the universe is in gases in deep space in the form of PAHs. And these are little tiny blobs, if you would, of carbon material, pure carbon. And they can have other things like nitrogen and so on sort of stuck in there too. And that changes the spectrum so it can be detected. And they're present in star formation regions. And so they should be present on what we think is a planetesimal-like body, like 3I. And they have been detected in comets. They have been detected in some of the asteroid samples sent back to Earth. I don't think they've been detected on the moon, but the moon has a fairly harsh environment, the surface of the moon. The PAHs can tell you something about the temperature of the environment that the object formed in. And that is, I think, really sort of why I really hope that we can find PAH emissions from 3I. We we generally think of comets as forming deep in deep space, and just so the temperature they were formed at was basically like 3 degrees Kelvin, or something like that. Of course, for something from cosmic noon, it'd be more like 6 degrees Kelvin. So it's not that much warmer, a little bit warmer. A redshift of 2, after all, or the equivalent of a redshift of 2. I think that the current data is sort of indicating that 3I was formed at a temperature of about 100 Kelvin, and that's fairly warm for star formation. And so that actually is somewhat consistent with a formation, in early cosmic noon. Now, PAHs could help confirm that, the discovery of PAHs. So that's why I hope they find it. And also, the alternative there would be, well, what if you just were like in a normal thin disk stellar system and you just happen to be closer to, this is a piece of something that formed closer to the star. Because after all, we know that some stuff formed fairly close to the sun, and presumably that happens with other solar systems, other stellar systems. And the I think that the chemical relationships we find could help to resolve that. And we shall see. I mean, I think this is a very exciting time here, and I really hope people find PAHs from this, and I really hope that we can then take that and use that to say something about the formation conditions of this object.
Now, the future. What can we do to be ready, since we have the Vera Rubin telescope coming online that will probably discover many more of these objects? What can we do to position something out there to catch the next 3I Atlas when it comes through, an object of great interest, and be ready and go and sit there and let it intercept us?
Well, so Ian Fleming, in his Goldfinger character and novel, said that once is happenstance, twice is an accident, 3 times is enemy action. And now this is not enemy action, but I think with one eye, a lot of people thought, well, is this going to happen a lot? Some people thought it was going to happen a lot, like immediately we'd be finding more, and well, we haven't really, one eyes. But with 3 of them, yes, we're going to find a lot. I think that's clear. I think there's no question of that. We're going to be finding a lot. With Rubin and the other surveys, Rubin in the southern hemisphere and surveys, improvement of the surveys in the northern hemisphere, we're going to find a lot of these objects. And yes, we do need to think about how we deal with it. And I've actually been thinking a lot about that, because it's apparent to me. I mean, for example, you come out of the blue and you go to a spacecraft operator who's running a, $1 billion spacecraft maybe, and you say, could you please do this, like your Oliver Twist or something? Can we have some more? Could you do something you're not intending to do? That needs some sort of structure, I think. That needs like the IAU or I don't know. I haven't thought that through that well, but some sort of structure where we say, these are the kind of objects we're likely to be seeing. Here's the kind of observations we would likely be take. Here's the priority we can give to them. I thought, for example, that it was just the simple fact is that 3i is going to be the opposite side of the sun. So spacecraft observations have to take that load. You can't just, otherwise, and it's only going to come through once. All of these objects are only going to come through once. That's really clear. We got one shot. Any data we don't collect will never be collected. There's no replacement there. There's no others going to come by in so many years or anything like that. They've all been different so far. And well, that may continue for a while. And also, by the way, so I've been thinking a lot about what 3i is teaching us in a sort of larger sense about dealing with new interstellar objects. I mean, Ian Fleming had his Goldfinger character say, once is a happenstance, twice is an accident, three times, well, he said enemy action, but three times is a pattern. We're gonna see more of these. I think that's clear. After 1i, some people thought there'd be lots of 1i's coming by, and some people thought, well, including myself, well, maybe not so many. We haven't actually seen another one, but with three of these objects, we're going to see a lot. Now, I got to make the point, sort of forcefully, that we have one chance with any of these. We have one chance with 3i. It's going to fly through the solar system. We can't stop it. It's going to go through. Once it leaves, well, potentially in the far, far future, we could send a spacecraft out there, like when we start traveling to Proxima Centauri or something. But for our lifetimes, we will probably not be able to get to this object. So that's it. I mean, we will get what we get, and that's all we're going to get. And so the real thing there is, we got to get the data we can. But on the other hand, we got get as much data as we can. But on the other hand, it's asking a lot of a spacecraft operator to just come in out of the blue and say, well, here's this thing. You need to observe it. Yes, you particularly need to observe it because you just happen to be in the right place at the right time. That's asking a lot. And I think it's really a testament that, people like me who are just sort of basically coming out of the blue, although I knew a number of these people already, but still, it's like, the UN didn't pass any resolutions. The Congress didn't pass any resolutions. The acting head of NASA didn't say, oh, we have to do this. Nothing like that. It's just people on the ground, so to speak. And I wasn't the only one by any measure. Were saying this needs to be done, and people started listening to it. And it would be good if we had some mechanism or some structure for that. So in other words, for example, suppose something like 3i comes by and it's on the Earth side of the solar system. Well, do we need to engage all the interplanetary spacecraft? Some, is it, can we rank observations like this? These would be nice to have, and these are essential. And when I say we here, well, who? Just the community? We're going to do this on YouTube or Facebook or something, or probably not. On the other hand, I would hate to say, well, it's got to go be reserved to the result, deferred to the IAU, and the IAU vote on it. I mean, that'll take a while, and that may not work that well. I don't know. I mean, actually, the next IAU meeting is coming up, and it would be interesting to have that discussion there. Like, how do you set sort of priorities and stuff? And I do know it's useful to have scientists say and write papers saying these observations would be good because they could solve these problems. Because I do know that I do think that the spacecraft operators find that very useful. That it's like they can say to why are you doing this? Is you just trying to score brownie points or get publicity or something? It's like, no, these scientists said that this is a good thing to do. And so, I encourage people to write papers on this. We got 3 months or 2 months, really 2 months, get out there and write. And tell, if you feel like I'm not writing it right, write a different paper. And, I think the more the merrier there. Because again, whatever we get is what we're going to have. And I actually think that people are getting this, and there will be a lot of data from this. I think you're going to have a lot of data from the Earth. You're going to have a lot of data from near-Earth spacecraft. and you're going to have data from the interplanetary spacecraft. And so, you know, a lot of people have been surprised by this and put in a lot of work. And my team, we worked on this pretty intensely for over 6 weeks. And that's a lot to just have something come in out of nowhere. And one, by the way, for which there's no funding. So, it's just like, we got to do this, not, this is something we just have to do and then go do it. So I'm really looking forward to seeing all this data that's going to be coming. And I'm really glad that I could play some small part in helping it to happen.
I have a sneaking suspicion that this caught the attention of a whole lot of astronomers. It's hard to ignore it because it's an interesting, in the very best case scenario, it is a fossil, from an earlier period in the universe. Worst case scenario, we figure out what it's not, or what anything like that. And we learn more about interstellar objects. It's sort of a brave new world of study because I think we're going to see a lot of these at this point, as you mentioned with Ian Fleming. And I wish you luck, and I hopefully you'll come back as we further explore interstellar objects. Thanks, Marshall.
Well, thank you very much. Thank you. Thank you for the time. And yes, it's exciting times here. I can't wait. It's like a Christmas present, right? That's coming early. I can't wait till December to see what we've got.
Absolutely. And everybody, there is a link to Marshall and colleagues' paper in the description below. Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.